So next on our list of definitions is heat of neutralization. Now, unfortunately, there is an experiment in this part that we will have to do at some stage when we get back to school, but it's a fairly simple experiment. There is a video which I will put up on the Google Classroom that will bring you through the stages of the experiment, and it involves a calculation, okay? But the experiment is very much a simple one, which I'll talk about in a few moments, but it just simply involves taking an acid and a base of equal quantities and equal molarity and bringing them together in order to achieve neutralization. Okay, and in achieving that neutralization, we're able to measure the heat change that takes place, and therefore we're able to extrapolate back then to get the heat of neutralization. All right, so I suppose the first thing we've got to remember is that there's a definition behind each of these. All right, now I did tell you when we were starting thermochemistry that the most important part of this section of the course are your definitions. So we already have heat of reaction, we already have heat of combustion, now we've got heat of neutralization. And the definition for the heat of neutralization is the heat change that takes place when 1 mole of H plus ions from an acid are completely neutralized by 1 mole of OH minus ions from a base. That's it, okay? But again, you'll hear it's the heat change that takes place. In fact, all of these definitions take the first words. It is the heat change that takes place. You begin all the definitions, except of course Hess's law, but you begin all the definitions with those set of words. The only one that doesn't refer to the mole is the heat of reaction, because in the heat of reaction, it's the heat change that takes place when a chemical reaction proceeds according to its balanced equation. All right, but all of the others, heat of combustion, heat of neutralization, heat of formation, they all refer to the heat change that takes place when 1 mole of a substance, and then you finish the definition according to the one that you wish to give. All right, so just keep that in mind. So there's the definition down at the bottom. It's the heat change that takes place when 1 mole of H plus ions from an acid completely neutralize 1 mole of OH minus ions from a base. Or put it this way, that's down here. It's the heat change that takes place when 1 mole of H plus ions and 1 mole of OH minus ions react together. Now, there is a video down here. There's a link to a video which just explains what neutralization is, and it gives you a visual as to what happens when you bring the H plus ions of an acid together with the OH minus ions of a base. I think it's self-explanatory because that yellow box up there tells you when you bring a H plus ion together with an OH minus ion, the inevitable result is a molecule of H2O, which is water. And of course, we all know that water is a neutral substance. Okay? So that's what neutralization is in a nutshell. I want you to consider the following reactions. I just want you to take a look at these. And again, remembering what I told you in previous classes on how to read these particular equations. See if you can read this yourself. How do I read it in perfect English if I was trying to tell somebody about this? 1 mole of HCl and 1 mole of NaOH will react together to give 1 mole of NaCl and 1 mole of water. Okay, so there's a 1 in front of all of these. It's like algebra. A coefficient of 1, there's no need to write it down. So therefore, if there doesn't appear to be a coefficient in front of anything, it's automatically 1. So 1 mole of HCl, 1 mole of NaOH react together to give 1 mole of NaCl and 1 mole of H2O. Delta H, the heat change for the reaction. Delta means change, okay? So the heat change for the reaction is minus 57.1 kilojoules per mole. Now, I hope you understand what that means. Minus 57.1 kilojoules means an output of 57,100 units of energy. That's what it means. So in other words, it's an exothermic reaction. And when you're reacting HCl with NaOH, it will feel warm to the touch. Or if it's not warm to the touch, it will be registered as a temperature rise on the thermometer should you have a thermometer in while neutralization is taking place. Okay, look at the next reaction. 1 mole of hydrochloric acid and 1 mole of potassium hydroxide react to give 1 mole of potassium chloride and 1 mole of water. The heat change for the reaction is minus 57.2 kilojoules per mole. Now that's extremely similar to the previous one. Okay, again, 57,000 units of energy are given out as this neutralization reaction takes place. Look at the third one. Let's change the acid. 1 mole of nitric acid and 1 mole of sodium hydroxide react together to give 1 mole of sodium nitrate and 1 mole of water. And the heat change for the reaction is minus 57.3 kilojoules per mole. And finally, if I change the base with the nitric acid, 1 mole of nitric acid and 1 mole of potassium hydroxide will give 1 mole of potassium nitrate and 1 mole of water. The heat change for the reaction is minus 57.3 kilojoules per mole. So there seems to be a very tight consensus on the amount of energy released during neutralization. And you wonder why that's the case. These appear to be 4 different reactions: hydrochloric acid with sodium hydroxide, hydrochloric acid with potassium hydroxide, nitric acid with sodium hydroxide, and nitric acid with potassium hydroxide. So let's look a little deeper into these equations and see exactly what's going on. Why are the heat changes for all these reactions almost identical, differing by 0.1 or 0.2 kilojoules per mole as we move down? Why is that the case? Let's look a little bit further. All 4 reactions are the same. Now, how do you notice that all 4 reactions are the same? They seem to be very different to me. Yeah, one has hydrochloric acid, one has nitric acid, one has sodium hydroxide, one has potassium hydroxide. But the heat change is telling me that these are very, very similar reactions. And I want you to think about why that's the case before I give you a hint. Okay, let's give you a hint. I'm going to highlight something here. Let's take out the ions that are not of any significance in this particular reaction. So I'm going to highlight them in green. Okay, so the sodium and the chlorine, the nitrate and the potassium, they will remain in aqueous solution. Now look at what's left after I've highlighted the Na, the K, the Cl and the NO3. Look at each of the reactions and look what's left in black. H plus OH gives H2O. H plus OH gives H2O. Now if you can't see it, watch. Let's take them away altogether. In each of these reactions, the fundamental reaction taking place is neutralization. In every one of the 4 reactions, even though they look slightly different, the chemistry is exactly the same. Hydrogen ions are reacting with OH ions, hydroxide ions, in order to form water. And if that's the reaction that is present in each of those 4, now it's no surprise as to why the energy change for each of those reactions is exactly the same. Because at the heart of each of these reactions is the same fundamental process of neutralization. Okay, so keep that in mind. So whenever you add 1 mole of H plus with 1 mole of OH minus ions, the heat change will always be in and around minus 57,000, minus 57, if you want to put it that way, minus 57,000 units of energy, or as we say here, minus 57 kilojoules of energy per mole of H plus and OH minus. Okay, so that's the fundamental principle that's at the heart of neutralization. And even though, let's go back 2 steps, even though it seems to be kind of hidden in these 4 reactions, as soon as we highlight where it is, like that and like that, now you can see it, that each of these reactions are fundamentally neutralization of a H plus and an OH minus coming together to give water. Okay, so by removing the spectator ions, now what's a spectator ion? Well, think about what a spectator is at a football game. A spectator is somebody who sits on the periphery of the field, watches the action, and the action is taking place on the field. So when we talk about spectator ions, we talk about ions that are in aqueous solution but not involved in the chemical reactions. Okay, so let's just go back to the previous slide there for a moment. The spectator ions are in green. So Na plus, Cl minus, K plus, NO3 minus. They're spectators because the chemistry in all 4 reactions here is between the H plus and the OH minus, and not the Na plus or the Cl plus or the K plus or the NO3 minus. Okay, the chemistry is not there. Now, how do I force them to react? Well, we take that a step further, and after we do the neutralization, we could evaporate the water, and then the Na plus and Cl minus would come together, or the K plus and the Cl minus would come together, or whatever the spectator ions are. So you'd have to force them to come together by evaporating off the water. But when you're a spectator ion, you're simply in aqueous solution as your ion, not involved in the chemistry. Okay, that's what we talk about there. So, by removing each of the spectator ions, we can see that the reaction that occurs in all 4 of the previous examples is H plus with OH minus ions giving you a water molecule. Okay, and that is at the heart of neutralization as far as this is concerned. So, this phenomenon does not occur when one of the reactants is stronger or weaker than the other. Now, if you go back to the 4 equations that were there, let me just quickly go back to the 4. The acid and bases that are mentioned here, there's something else about them. HCl is a strong acid. NaOH is a strong base. KOH is a strong base. NO3 is a strong acid. So in this case, not only is the chemistry between H plus and OH minus, But the 57,000 units of energy that are given out from this particular chemical reaction happen when it is a strong acid reacting with a strong base. And that's the key thing. So should I change the strength of an acid? Well, then we're in trouble. We're not going to get the minus 57,000. So if I was to use, for example, ethanoic acid, which is the ingredient of vinegar, that's a very weak acid and it has partial dissociation. So therefore it's not able to produce as much H plus as these would, and therefore the energy change would not be the minus 57,000 units that we see in these four reactions. Okay, so minus 57,000 units of energy in the exothermic neutralization only occurs when the acid and the base are strong acids and strong bases. Okay, so keep that in mind. So let's go back to the slide around there a moment ago. So this phenomenon does not occur when one of the reactants is stronger or weaker than the other. So take this for example. HCl, strong acid. NH4OH, ammonium hydroxide, it's a very weak base. Okay, so now you've got a strong acid with a weak base. The acid will produce the amount of H plus that you require, but the base, the NH4OH, is not going to dissociate very well and therefore can't give a matching cohort of OH minus ions to neutralize completely the H plus. So in a situation like that, we don't have complete neutralization. Watch the energy, minus 52.2. Okay, it's less. It's less than what it was a moment ago, because it was minus 57 a few moments ago. Okay, one more. CH3COOH, ethanoic acid, the staple ingredient of vinegar. About 5% of all vinegar solutions are ethanoic acid. Okay, so ethanoic acid, which is a weak acid, and we should know it's a weak acid because it's edible, and NaOH, which is a strong base, react together to give sodium ethanoate. Now we'll talk more about that when we come on to esters next year, and water. So what happens here? The NaOH being strong, let me just write this down. So this is the strong one. That will dissociate, break up fully. That will give you a full cohort of OH minus. But unfortunately, the acid is weak. And by being weak, it does not produce the required amount of H plus. So therefore, there is not complete neutralization. We will not get minus 57,000 units of energy given out. In fact, in this case, what do we get? We get minus 55. It's still less. It's not the minus 57 that we're used to when we have a strong acid and a strong base. So if you have a strong acid and a weak base, do not expect minus 57,000 as your energy change. If you have a weak acid and a strong base, do not expect minus 57 as your energy, minus 57,000 units as your energy change. If you have a strong acid and a strong base, you will get minus 57,000 units of energy given out in the exothermic process. Okay. All right. So when a weak acid or weak base is involved in the neutralization reaction, as I've told you already, their levels of dissociation. Now, the word dissociation simply means break up. Okay. When something dissociates, it's, for example, HCl dissociates into H plus and Cl minus. It just means it breaks up. Okay. It's a natural phenomenon that occurs when you put certain substances into water. When you make an aqueous solution of HCl, you will get complete dissociation. So a strong acid is one that breaks up fully. A weak acid, only very few of their molecules break up, so therefore the amount of H plus that they produce is not what is required to get to the minus 57,000 kilojoules of energy for that particular reaction. And the same with a base. A strong base gives you a full cohort of OH minus, whereas a weak base will only give you a limited amount of OH, and if you're dealing with a limited amount of OH, you're not going to get the minus 57,000 as the jackpot. Okay, so more energy is required to produce 1 mole of ions from these weak molecules. So therefore, the heat of neutralization will be less than the required minus 57 kilojoules per mole. So in other words, what I'm trying to say there is that if we do want to get 1 mole of H plus from a weak acid, then we've got to put energy into the system to break them, because they're not going to do it by themselves. Okay. And likewise, if I want a weak base to give me 1 mole of OH minus ions, then I've got to put energy into the system to break them up into the required quantity, because it ain't going to happen by itself. So weak acids and weak bases are problematic in chemistry. They dissociate very badly and they need more energy. So if you have to input energy before you get neutralization, well then that's going to lower the amount of energy given out by the system, as a result of the neutralization. Okay, I hope that makes sense. I hope it's logical enough for you. So what's the experiment involved here? The experiment is to measure this heat of neutralization. Okay, now we're doing this in a laboratory in a second level school with styrofoam cups and a thermometer open to the environment. We will not hit minus 57,000. We want to try and get as close as we can to it. So what I'm going to give you when we get back to the lab, or if we were in the lab, would be, for example, 50 centimeters cubed. Let's think about this. We would have 50 centimeters cubed of 1 molar HCl and 50 centimeters cubed of 1 molar NaOH. Now, there's two things, well, actually, there's three things you should notice here. Number one, same volume, okay? The same volume. Number two, the same molarity. Number three, the same strength. So these are strong acids and bases. So HCl is a strong acid, NaOH is a strong base. So they are perfectly matched. In fact, everything about them is equal. We're putting in the same volume of the same molarity of the same strength acid and base. They are matched perfectly. HCl will give you a perfect cohort of H plus ions. In fact, we're going to work that out in a moment. And NaOH will give you a perfect cohort of OH minus ions. Now, let's just work out exactly what we would get. If both of these are 1 molar solutions, that means that if I had a litre of both of these, I would have 1 mole in that litre. Now, I don't have a litre. I've only got 50 centimetres cubed. So I've got a 20th of a litre, which means I will have a 20th of 1 mole of those ions floating around in both beakers. I hope that makes sense to you. Okay, so if it's 50 centimetres cubed of 1 molar HCl and 50 centimetres cubed of 1 molar NaOH, then we have a 20th of a litre, which will contain a 20th of a mole. Okay, just keep that in mind. That's your stoichiometry coming back to bite you. And I did warn you, when we were doing stoichiometry, it's going to be everywhere from now on. So 1 molar means 1 mole in a litre. So if I had a litre, I would have a mole. I don't have a litre. It's wasteful. I only need 50 centimetres cubed. So I have to reduce the number of moles times 20 to get a 20th of a mole. Okay, and 1 over 20 in decimal form works out as 0.05. So in both of these, I am using 0.05 moles of H plus and 0.05 moles of OH minus. See that? So because both of them are strong acids and strong bases, they will give me a complete dissociation, giving me 0.05 moles of H plus and 0.05 moles of OH minus. Now, they're perfectly matched. So these two will react together to give you water. And there will be nothing left in excess. Every H plus will have 1 OH minus to bond with, so there'll be nothing in excess, meaning that I can expect an energy change of minus 57,000 units of energy, or put it another way, minus 57 kilojoules in this particular reaction. Now, the problem is it's kilojoules per mole. So what this experiment is actually going to give me is not kilojoules per mole, it's going to give me kilojoules for 0.05 moles, because I'm only using 0.05 moles. So therefore, when I register the heat by means of a thermometer, and I plug it into the formula which I'll speak about in a moment, the heat change that I'm going to experience will be the heat change that's only given by 0.05 of a mole. So I'm going to have to bring it, multiply it by 20 to get it back to 1 mole, multiply the heat that I get in this experiment by 20, and it should bring me very close to the target value of minus 57,000 units of energy. Okay, so that's the experiment that we do. Now, let me just get rid of that, because there's a formula that we have to know. And the formula is E equals mc theta. Okay, now E is the energy. Heat is energy. Do you remember I told you that before? Heat is energy. So in this case here, the energy, the heat that we're going to experience in this reaction is equal to the mass of the liquid that is in the beaker after neutralization. Now, what liquid is in the beaker after neutralization? The answer is water. Okay, so this is the mass of water in kilograms, and it must be in kilograms. This is what we call the specific heat capacity. Now, the specific heat capacity of any substance is the amount of energy that is required to bring 1 gram of that substance up, 1 kilogram of that substance up 1 degree. Okay, so keep that in mind. That's the specific heat capacity. They use it in physics far more than we use it in chemistry. But just be aware, it's the amount of energy that is needed to bring a kilogram of substance up 1 degree. Okay, and then we have theta, which is the temperature change. Okay, the temperature change. So in other words, if I begin my experiment at 20, and after the experiment has gone to 23 degrees, then the temperature change would be 3. And we use those 3 readings in that formula to reveal the energy that has been released by, remember, the 0.05 moles of acid. All right, so keep that in mind. And then we can multiply both sides by 20 to bring it back to a mole. So let's have a look. Okay, so to measure the heat of neutralization of HCl and NaOH, that's what we want to do. Equal numbers of moles are mixed in a foam container. Now, equal number of moles of HCl and NaOH. There's another equality here. They are both strong. You couldn't do this with a strong acid and a weak base, or a weak acid and a strong base. If you're going to do it, you're going to use a strong acid and a strong base. Okay, so equal number of moles. In this case, 0.05. We're using 50 centimeters cubed. So we're using 50 cm cubed of 1 molar acid and base. Now please keep in mind, if it's 50 centimeters cubed of 1 molar, that means if I had a litre, I'd have 1 mole, but I have 20 times less. So I'm going to have a 20th of a mole, which means that in the 50 centimeters cubed, there will be 0.05 moles. That's what that means. Okay? E equals mc theta is used to calculate delta H, the heat change. Okay, so E is energy, M is mass of water in kilograms, and C, as I told you already, is the specific heat capacity. Now, the lovely thing about this question is they have to give you the specific heat capacity. Now, specific heat capacity of what? Well, what's in the beaker after the experiment? If we've added the acid and base together, what have we got? We have water. So it's the mass of water in kilograms multiplied by the specific heat capacity of water, which they will give you, multiplied by the temperature change, which you're going to get on your thermometer. Okay, so there's your C, and they'll give you 4,200 joules per kilogram per Kelvin. Okay, so they'll give you that figure, and theta then, theta is the temperature rise, which will be measured on your thermometer in terms of degrees Celsius. So C is the specific heat capacity. We've talked about that already. It's the energy required to bring 1 kilogram of any substance up 1 degree. So for example, if you were to take a bag of sugar, okay, a bag of sugar is 1 kilogram. If you were to put that on a hot plate and put a thermometer into it, as soon as you recognize the fact that it has gone up 1 degree, the amount of energy required to do that is its specific heat capacity. Okay, so in this case here, we have a value of 4,200 joules. So that's telling me that if I want to get water, 1 kilogram of water, to go up 1 degree, I would have to give it 4,200 units of energy. That's exactly what the specific heat capacity is. But don't worry too much about it. Just know you're going to have to use the figure in any given calculation. So here's what we do if we had beautiful electronics on our side. We would take a cup into which we would pour the acid and the base. Now we've got to be very, very careful. If we're measuring temperature rise, we have to make sure that the 2 liquids begin at the same temperature. So we've got to let them sit on the base with 2, at the bench I should say, with 2 individual thermometers. Okay, when both liquids, when the 50 centimeters cubed of both liquids has reached the same temperature, only then do we add one into the other. Do not add them in together if they are at very, very different temperatures, because then what's going to happen is one is going to rise, one is going to drop, and the recording is going to be all over the place. So you leave them until both of them agree on a common temperature. And once both of them are at a certain temperature, you pour one into the other and you watch the thermometer record the energy change. Okay, so you very carefully watch your thermometer. You will have recorded what the starting temperature is. You'll then record what the finishing temperature is, which is always given by the highest point that the mercury will go to, or the alcohol will go to, in your thermometer, and then you use your formula. So in this case here, the thermometer is replaced by a probe. That's all this is telling you. So this is trying to, this probe here, this thing that we have, see that? That's a probe that will give me joules. All right. Now I still have my thermometer because I'm old-fashioned. I like thermometers. I think it's important you're able to read one. So you still have your thermometer, but this thing here is going to be able to read the number of joules that are present. All right. And also what it will do is it'll give, if we required it, it would give heat. So it can be a heater as well as being a probe for registering heat change. But we're going to use a thermometer, so stick with that. So what do? Well, we use a foam cup. Okay, because we don't have the technology of a nice joule meter. So we're going to use a foam cup. So all that we do is we take 2 foam cups, one there and one there. Okay, we put in our 50 centimeters cubed of HCl. We put in our 50 centimeters cubed of NaOH. Now 50 centimeters cubed of both, don't forget, because it has to be equal volumes of equal molarity of equal strength. Okay, so therefore we've got 50 centimeters cubed of HCl and 50 centimeters cubed of NaOH. So we test both of these to see what their starting temperature is. And if both of their temperatures are the same, then we pour one into the other. And when we pour one into the other, this is the result. Here we will have 100 centimeters cubed of water. And that's important because we're going to get some measurements from that in a moment. Here we will measure the temperature rise. Now, why into a polystyrene cup? Because a polystyrene cup is a cup that insulates. It's an insulator, meaning that it will keep any energy that tries to escape, it'll keep it within the confines of the system, okay, and won't let it out. Now, you're probably saying, well, it's open at the top. You could, if you wanted to, put a lid on this thing. And that's one of the little enhancements you could make. You know the takeaway cups that we get, and we put little takeaway lids on them? You could use one of them if we had them. Now, we don't have them. But a lid, again, would be a good addition because it would help us to keep the energy that's produced in the system so that the thermometer can see it and register it for us. Okay? So these little changes, they all enhance the experiment as we go along. It's a second level school. Foam cups are as good as it's going to get, and foam cups that are obviously open to the atmosphere. But they will ask you at the end of this experiment, what modifications could you make to improve your result? One of them would be put a lid on the damn thing. Okay, simple as that. Put a lid on it. Use a more accurate thermometer, etc. Okay, got that? That's it. That's done. Okay, so you pour. Oops, let me get rid of my writing because I've got your little animation here. I didn't realize I had. So you pour your 50 centimeters cubed of base into your 50 centimeters cubed of your acid, and then you watch the rise in temperature. Simple as that. And when you get your rise in temperature, that will be the highest point that it goes to. You then use M, C, and theta. Okay, you're going to measure the rise in thermometer on the thermometer, rise in temperature in the thermometer, I should say, and then you're going to take 100 centimeters cubed of water as your final result. So now what have we got? We've got a specific heat capacity which will be given to us. We have a rise in temperature which we have recorded on the thermometer because we've recorded our starting temperature and our finishing temperature, and we now know that in the beaker is 100 centimeters cubed of water. So let's go to the formula. E equals mc theta. Mass, I told you, has to be in kilograms. And look at the questions just come in there in red at the bottom. What is the mass of this solution in kilograms? I hope you can remember what the density of water is. The density of water is 1 gram per centimeter cubed, meaning every centimeter cubed has a mass of a gram. So if I have 100 centimeters cubed, that is going to have a mass of 100 grams, which in kilograms is 0.1 kg. And that is what's going to go in there for M. Okay, so you've got 50 centimeter cubed of acid, 50 centimeters cubed of a base. You pour them in together, you get 100 centimeters cubed of water. And don't forget, it's the measurements of the final solution that we're using. 100 centimeters cubed of water has a mass of 100 grams because its density is 1 gram per centimeter cubed, which in kilograms is 0.1. So there's my M calculated. What's C? It's given to me. In this case here, it's 4060. Now, it can fluctuate from year to year, so make sure you use the value that they give you. Okay, 4200, 4060, doesn't matter. Use the value they give you. So that will be given. And then the last thing we've got to do is to simply say how many degrees on the thermometer did the temperature rise? And you put that in here. And keep in mind that the energy you will get will be the energy that has been given out by 50 centimeters cubed of the 1 molar acid. which in fact is 0.05 moles. Okay, so we expect something very, very small. Okay, so here's a sample result in a sample calculation. First of all, the mass of the water, as we already said, 50 and 50 gives me 100. 100 centimetre cubed of water is 100 grams, which is 0.1 kilograms. We've got that. The specific heat capacity is given to me in the question as 4060. And let's say, for example, now we got a rise in 7 degrees. So it started at 20, and by the time you were finished, it had gone to 27 degrees. The rise in temperature is 7. Bring in my formula, E equals mc theta. Multiply the kilograms by the specific heat capacity by the change in temperature to get this, 2865 joules. Now that's a hell of a long way away from my 57,000. But please remember that the energy that's been given out here is the energy given out by 0.05 moles, because we only used 50 centimeters cubed of a 1 molar acid. And 50 centimeters cubed of a 1 molar acid only contains 0.05 moles. So that means I would have to multiply this by 20 to figure out how much energy would be given by 1 mole of the acid and base. Okay, so this is for 50 centimeters cubed of 1 molar HCl, which we've already said, and we need to find out the heat change for 1 mole, because that's what the definition says. The heat of neutralization is the heat change that takes place when 1 mole of H plus ions completely neutralize 1 mole of OH minus ions. Okay, so we have to get to 1 mole, because only then will we have the heat of neutralization. So keep in mind that 50 centimeters cubed of a 1 molar solution is 0.05 moles. So if I want to bring 0.05 moles up to 1 mole, I've got to multiply it by 20. So therefore I'm going to multiply this figure here by 20, and lo and behold, look what I get. I get 57.3 kilojoules per mole were given out in this experiment, which is exactly the bang-on figure for the energy change for 1 mole of an acid with 1 mole of a base when neutralization takes place. Okay, now don't worry about the minus, because in this case we're registering 57.3 kilojoules. We're registering that, and it is per mole, so don't worry about the minus. Okay, that's it. What I'm going to do, I'm going to leave you with that, but I'm going to put up a few sample questions in relation to using that calculation. I'll put these sample questions up on Google Classroom along with this particular video, and the set of slides for the whole thermochemistry, I'll put them up as well. And I want you to go through the calculations. E equals mc theta. M is the mass of water in kilograms. C will be given to you in the question, and theta is the rise in energy. And please remember that E will always represent something far less than a mole. You always have to bring that back to 1 mole when you're dealing with your questions.